Hello students, today I am back again with the explanation of the second part of the chapter Magnetic Effects of Electric Current. So let's begin. Today our first topic of discussion is magnetic field due to current carrying in a circular loop. Here we can see a circular loop and current is passing through it as we see that there is a battery attached to this circular loop. When current passes through a circular loop or conductor, the magnetic field produced in it is in the form of concentric circles around the conductor. Towards the center of the arc, the circles becomes larger and appears as a straight line. That means here we can see at the middle of this circular loop, the two magnetic fields, they converge and we see a straight line here. We all know about the concentric circles. Concentric circles are circles which have same center but different radius, and we can see the magnetic field at this part and at this part also, that all are concentric circles. Now we are going to learn about solenoid. A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. We can see the picture of a solenoid here. The solenoid produces a magnetic field when electricity is passed through it. That means whenever we pass electricity through this coil, we will get a magnetic field around it. The structure of magnetic field can be seen here. With the help of a bar magnet, we can also determine the poles of this current carrying solenoid. We will get one north pole and one south pole. The strength of the magnetic field around this solenoid or around this current carrying solenoid depends on two factors. One is the strength of the current. That means more the amount of current we pass through the solenoid, the stronger the magnetic field becomes. And secondly, if we increase the number of turns in the solenoid, then also we get a increased strength of the magnetic field. Our next topic of discussion is electromagnet. A strong magnetic field inside a solenoid can be used to magnetize a piece of magnetic material like soft iron when placed inside the coil. Such a magnet is called electromagnet. That means we have a soft iron core, and when electricity is passed through the solenoid around it, we get a magnet. But as soon as we switch it off or stop the flow of current, this nail or this soft iron core loses its magnetic ability. So it has plenty of uses. We can increase the strength of the current to get a magnet of higher power. We can switch it off when it is not in use, and moreover, by changing the poles of the battery, we can change the polarity of the magnet. So there is a huge amount of use of the electromagnet. Now we are going to learn about force on a current carrying conductor in a magnetic field. First, let us observe this picture. It contains a conductor AB connected to the two ends of a battery. So when the switch is closed, electricity flows in this direction through the conductor. Since electricity is passing through it, there has to be a magnetic field around it. Now, if we place a horseshoe magnet around it as shown in the figure, the two magnetic fields will interact with each other and we will see a deflection in this current carrying conductor. Now, if we change the polarity or the poles of this horseshoe magnet, we will see the deflection in the opposite side. The deflection of this current carrying conductor depends on many factors. First of all, current. We can increase or decrease the current, which will also increase or decrease the force acting on it respectively. We can change the polarity to change the direction of force. Similarly, we can change the poles of this magnet in order to change the direction of force. We can see the pictures of all the situations that can arrive that we can get is given here. Now we are going to learn about Fleming's left hand rule. In the last topic, we have learned that a current carrying conductor placed in a magnetic field experiences a force. Fleming's left hand rule helps us in connecting the direction of force, the direction of magnetic field, and the direction of current. Here we can see a picture of our left hand. Here it is told that if we stretch our thumb, index finger, and the middle finger in mutually perpendicular directions, then the thumb will represent the force, the index finger will represent the magnetic field, and our middle finger will give us the current. Here we can see that whenever this current carrying conductor will be placed in a magnetic field, it will experience a force in the upward direction. So if we know any two of the directions, we can identify or determine the direction of the third with the help of this Fleming's left hand rule. So this is the end of today's explanation. I hope all of you have understood the topic clearly. Until next time, take care.